binary versus text files. What are the differences? If I come here to my code editor and I create a new file, which is here already, and I type in, for instance, hello world, how are we doing today? Or just how are we today? Just to keep it shorter. I'm going to save this file to my code folder and call it hello. Hello, let's say hello.txt. It doesn't really matter, but just to say it's a text file. So this is a text file, right? I can open it in my code editor. It contains text inside. Now, what about a file that would be like an image, a picture, a photograph, or another file that would be a music file, or a zip file even, which has multiple other files inside it, both binary files and text files mixed together, all right? So what really is the difference? Well, in order to understand that, we are going to use a Hex Editor. So it's called a Hex Editor. And here for Linux, I found that we can install one that is called ghex. So ghex. So you can install it with these commands. So sudo apt-get install ghex. And I already installed it here. So if I run, it doesn't do anything because it's already installed. So go ahead and install it, and afterwards you can go here to show applications and type in gh or ghex, and then you open it, and it's gonna just open this little window, and I'm gonna go here, file, open, and I'm gonna select that text file that is actually open here in Guinea. So if I open that, it's going to show this screen, and if you're not used to a Hex Editor, which I suppose you're not, you're going to ask yourself, what the crap is this? Now, I want to make this just a little bit more wider here, so that I have this gray bar dividing what is here on this left side from the right side, right? So you maybe want to do that. So you see that it's kind of a weird behavior it has there. All right, so I want to keep it, yes. So that's a good size. And we see here on the right side, it's written kind of exactly what is on the file that I created, but it's not exactly the same. So it's hello world, exclamation mark, and then there's a line break, but the line break is not here. Instead, there is a dot. And then how are we today? And then there's the final interrogation mark, and then there's a dot. So what is this? And what are these numbers here? So remember, this is a text file, and in fact, this is also a binary file. But let's talk about that later. So what is a text file? It's just characters. So you see this, if you think about an array we already saw in previous videos is like a sequence of things. It could be a sequence of numbers. So let's say we have, I'm going to create a new file here. Let's say we have a Ruby code that is an array. I have to save it so that it highlights this as Ruby code. Some Ruby code.rb. All right. And if I type in here 48 and then 55, you see this is kind of the same thing as this. So this is an array. This is in fact a big array. So any file, and this is important, any file is just like a big array, or just an array, really. Could be a small file, like this file is small. It's this small. In fact, if I go to my code folder and I list, if I press ls minus L without the H, we're gonna see this number here, and this number here is the size of the file, which means the amount of bytes that it has. So it has 31 bytes, all right? 31 bytes. And here we are seeing each one of these 31 bytes. So 48 is the first byte of this file. And 65 is the second byte. And so on until the last byte. So 0A is the last byte of this file. And then you might be wondering, what is 6C? What number is 6C? Or what means 6C? Well, 6C is the contents of the third byte of the file, right? But what is 6C? And what is 0A? What are these letters here? So to explain that, I have to explain a little bit of math and a little bit of number notations. So this should not be very complicated, and I'm gonna try my best to do it here. So you see, if I select, let's select this weird one here, so 6C. 6C, and then we select it here, and you see that these numbers down here, they change. So if I select this thing versus, well, this is the same actually, but if I select the 65, we see that these numbers change, all right? So here, and the important ones that, actually the most important one we want to pay attention now is to this one, unsigned 8-bit, and then it says 108. And 48, so 48 here is 72. So how come that 48 is 72? Well, and what about 8-bit, all right? What about 8-bit? So to explain that, I'm gonna open IRB, which is gonna let me run some Ruby code. Let me press Ctrl L to clean the screen, and let's go with 72. So 72, let me put this here. So I selected 48, and then there's 72 here. So if I type in 72, I'm gonna get 72, all right? Now, what if I type 72 string? I'm gonna get the string 72. So that's expected. Now, how do I convert this to an integer, right? So this is a string, and for us to convert this to an integer, we use to_i, all right? And then we see now this is an integer. So we already saw this in previous lessons, and I'm not gonna go through that again. Now, there's something implicit here in to_i, and what that is that there's an implicit parameter 10 here. So if I do this, I'm gonna get that, and if I do this, I'm gonna get something different, and I'm gonna keep getting different numbers here, and then you wonder why, what those numbers are. So 93, and then 14, I'm gonna get 100, and if I 15, and then 16, and so on. Now, what is really interesting here is the 16 part. So let me show you something. We have the numbers, usually the way we count them, they go from 0 and then 1, and then they go all the way to 9. So whenever you want to express any number that is 10 or larger, you have to use more than one digit. It's impossible to represent 10 in a single digit, because our numbers go only from 0 to 9 in one digit. And if you go 9 plus 1, you're going to have an 1 here, and then you're going to have a 0 again. So you restarted it. And then you're going to go and change only one digit 10 times. So from 0 to 9, those are 10 times, all right? So there is something there, and that something is the number 10. So the notation of the numbers we use, that we call decimal numbers, right? So deci from 10 is the reason for this. But there's a different notation that is very, very important in computers in general, in software in general, which is the hexadecimal. So hexa from 16, hexadecimal, actually hexa from 6, but hexadecimal then from 16. And that's something where you have, instead of having 10, so instead of having from 0 to 1, 3, 4, I'm going to do the whole thing here. So instead of having 10, you have 16, all right? But the question then is, which symbols do you use to represent that? So let's pick up the alphabet, the first letters of the alphabet, until we have 16. So 13, D, E, F. So you see A, B, so 0 to 9, and then A to F. And these, remember, these are numbers. So these are numbers. And if you're not understanding what I'm talking about, is that if we represent a number in a hexadecimal notation, we are going to have each digit goes, like in a decimal or in a normal notation, each digit, like 0, would go from 0 to 9. So 9 is the highest. But in a hexadecimal notation, each digit would go from 0 to F. All right? So 0 is the lowest one, and F is the largest. And then F, and then I can do math with this. So F plus 1 equals 1, 0. And 1, 0 is not 10. 1, 0 is actually 17. All right? So think about it this way. 0 is 0, 1 is 1, of course, 2 is 2, and so on until 9 is 9. And the number 8, the number A is 10. All right? So if we convert this to a decimal, is a 10. And then this is a 11 and 12 and 13 and 14 and 15. And I said this was 17. I was wrong. It's 16. So this is 15, 0 to 15. There are 15. Wait. 9, 10, 11, 12, 13, 14, 15. Yes. So 15 plus 1 is 1, 0. Is 1, 0. And 1, 0 is 16. All right? So in most programming languages, and Ruby included, you can represent hexadecimal numbers. So these bytes here, all these bytes, they are represented in hexadecimal number. They are they're not a different number, they're just represented this way because it makes it actually easier. Once you get this, once you get used to it, it makes it easier. So 48, for instance, 48. If I type in Ruby 48, I'm gonna just get 48. But there's a special notation for hexadecimal numbers that I can type in 0x. So 0x is special. There is no 1x, there is no 2x, there is only 0x. All right. So 0x, and then the number is gonna be 72. And this is exactly what we're seeing here. So 72. And let's go to, let's say 0a, which is saying here is 10. Well, that one, so 0x0a is 10, which is the same as saying only 0xa, all right? Because if you write 1, you write 1. You don't write zeros in front of it. You don't write zeros in front of any number. So 0x0a is 10. And if you look at our array here, we have A here as being 10. So 9, 8, 9, 10. All right. And then a B, so 0, 0x 0b, and I don't need a 0, is going to be 11. And 0xf is going to be 15. And 0x10 is going to be 16. So why is this printing 16 here and not 0x something? Well, because actually this is just, as I said, this is just a number. This is just an integer. And if you do this, they're the same thing, all right? And this is just a different way to represent this. And Ruby is never going to show you a hexadecimal number here because it doesn't make sense. And it doesn't, also Ruby doesn't know that this is a hexadecimal number. I mean, this is the representation of the integer, but once it is inside Ruby, Ruby doesn't have a way to know, and it doesn't really matter where this number, whether this number came from a decimal notation or a hexadecimal notation. All right. So yeah. So if you want to understand more about hexadecimal numbers, more than that, I'm going to explain a little bit more later. But I encourage you to go and look for content on that. I cannot explain here much more than that. All right. So it should be simple. Maybe in the beginning it's not that simple, but the basic idea is just a different notation on numbers. Now, you wonder why, I want to go ahead and why are hexadecimal numbers used? All right. Well, because the reason is because like how many numbers can you represent? And let's now for a while forget about hexadecimal numbers. How many numbers can you represent in with one digit? Well, you can represent 10 different numbers, right? From 0 to 10, or rather from 0 to 9. So of course from 1 to 9 there are 9 numbers, and then there's also the 0, so it's 10 possibilities. How many numbers you can represent with 2 digits? Well, we can represent 100 numbers with 2 digits, right? Because in the first position, so let's say 0, 0, in the first position we can have 10 possibilities, and for each possibility here we also have 10 other possibilities in the second digit. So that's 10 times 10, which is 100. And if we would have 3 digits, that would be the same thing, 10 times 10 times 10, so 1,000. Now in hexadecimal, a single digit can represent 16 different numbers from 0 to f. And how many digits can we represent? How many numbers can we represent with 2 digits? 2 digits. We can represent 256 different numbers. Now this number is important. This number you're probably going to see a lot if you're dealing with binary data, and yeah. And what is special about this number is that if you think about I just told you about decimal notations, where you go from 0 to 9, all right? From hexadecimal, where you go from 0 to f. And there's a different notation which goes from 0 to 1. 0 to 1. And this is binary notation, all right? So you only have zeros and ones. So you only have zeros and ones. So if we say a number that goes, so 256 different possibilities. So from 0 to 255, we have 256 numbers. All right, do you agree? if it from 1 to 266, we have also the same number of numbers. And if we change this to 0, we have to also reduce 1 here. And now one thing is that if you do 255, how do we know which number is this in hexadecimal? Well, remember, we have this thing implicit here. Oops, I have to do it as a string. But if we pass in this number is FF is 255. So the thing is, well, of course, right? So we have here 16 possibilities and here 16, and then you multiply, and then we are going to have 256 because we also have this 0, 0. So 255. So that's the maximum number we can represent with 2 digits, and the lowest one is of course 0. And between these, including 0 and including 255, we have 256. Now, what is special about 256, 260, is that, and now let me show another thing that is implicit in Ruby, is that if you convert a number to a string, there's also something implicit here. You're saying that is base 10. Base 10. A decimal number is base 10. A hexadecimal number is base 16. And then we can see it's FF. There's no difference between uppercase and lowercase, all right? So FF. Now, if we convert this to 2 is going to be binary, because binary has only zeros and ones. We are going to see this beautiful number, which is 4 ones here and 4 ones here, all right? So these 4 ones are this F, and these 4 ones are this F. And what we have here is we have 8 bits. So this is, we call this a bit. And a bit is the lowest, let's say the smallest unit in a computer, in a modern digital computer. So maybe you already heard about that computers, they deal with binary data, only with bits, zeros and ones. Yeah, so a bit can either be 0 or 1, and you can use different terms to that. You can use like a bit can be something or not something. So it's always 2 possibilities, all right? So it's either true or false, is on or off. And if you go to, the reason this comes from the electronics, the way electronics and the way that Boolean logic works, but I'm not gonna go down there, but just the reason for that is that computers, they operate on high energy levels and low energy levels, and you could say, okay, high energy level is 1, low energy level is 0, and then you can make all sorts of computations with that. And we see these also here in software, which is at the same time far away from electronics because you don't have to learn it in able to do software, but it's, after all, it's tied to how the circuitry works. All right, so there is a convention, and why I'm picking this number, why I'm picking 2 here. You see here is also, why is not 3? Why do they come in pairs? Why are these digits, why is there always a space in here? Why is it not 48, 6, 5 without this gap in here? And the reason is that 8 is a special number, and it's just a convention. It's just because of convention. So we have a bit can be 0 or 1. So the size of it is 2 bits, 2 possibilities, all right? And a byte a byte is composed of, I think this does make sense. A bit can be either, it has length 1, all right? And a byte has 8 bits. A byte has 8 bits. And the amount of information you can represent in 8, 1, 2, 3, 4, 1, 2, 3, 4, and then we convert this to a integer, and this is base 2, because it's binary, and it's 8 bits, is 255, which with a 0 is also 256 possibilities. Oops, that didn't go right. Yeah, convert it back to hexadecimal. So this is the reason. This is the reason for it. And this is why we have here always in pairs. You're always going to see bytes in pairs, because you can write a byte in 2 hexadecimal numbers. And with 2 hexadecimal numbers, you can represent all the possible bytes that are out there. So this is the byte 41. All right, so enough with this math explanation, and back to the file here. So 48 is a byte, and its decimal value is 72. And we see that it's also the H, all right? So hello world here. And this the 65, I don't know why I keep saying 55. So 65 is an E. An E. So what is the connection? What is the connection between these numbers and these letters? Well, let me do something slightly different here. Slightly different. Let me put in here the alphabet. So A, B, C, D, E, F, G, H. I don't want to put everything. Okay, I said I didn't want to put everything in, and now I put everything. Now I'm going to save the file, and I have to reopen here. So close and open again. And now we see here the alphabet. And we see that A is 61 in hexadecimal. And we see that B, you see that it's highlighting there, is 62, and then 63. And you can clearly see that there's a sequence here, all right? 69, and then 69 plus 1 is 6A, 6A. You see here the decimal notation is 105, and then 106, all right? And yeah, so on until the Z, and the Z is 122, or 7A in hexadecimal notation. So if you stop to think about it, I told you before that this is a text file, but I told that it's actually also a binary file. And if you think about it, it's about binary data here. You see, this 48 is 72, but the binary representation of it is this. So it's showing you here the binary representation, which is always 8 bits, all right? So if you think about it, a file is nothing more than an array of zeros and ones. And the zeros and ones, they always come in packs of 8. So you the file size in bits is always going to be a multiple of 8. All right, but that's maybe only more confusing than it should be. But what about this relation here from 61 to A and then 62 to B? Well, this is also a convention. So as I said, the reason for 48 being like 8 bits is just a convention. Maybe there's a better reason behind, but after all, it's a convention. And the reason that A is 97 in decimal is also a convention. Is a convention. And I'm going to explain more about this in the next video, where I'm going to talk about text encodings. So the way you encode text. But here we can already see a little bit of text encoding. So the way you encode the text on a binary file is that you have a convention. You say that A or small a is the number 97. And everybody's going to accept that. Everybody's going to say, okay, when I see 97 in a file, it's small a. And a B is going to be 98. And a Z is going to be 122. So everybody accepts on that. That's like internationally accepted. And if you want to say, for instance, like I don't like the fact that small a is 97. I want to call it I don't know, 50. Well, you're going to have a problem, because you're going to have to convince everyone around the world, or everyone doing machinery, computers and stuff, that an A is going to be a 50. So you're going to have a big problem, and you're probably not going to want to do that. So A is 97. That's just what somebody said, and it's like that until today. And then we have here also, we see that, let me pick here the H. So here, H. So H from how are we? So this small H is 104, but we can see that the big H is 72. Of course, because they are different characters, they need to have different numbers to them. Otherwise, if they wouldn't have a distinction, there would be no way to know whether this would be a big or a small letter. All right. So there are these numbers, and this number here always goes from 0 to 255. All right. Remember that, because we have two hexadecimal numbers, and the number of possibilities is 256, which is from 0 to 255. Now, we don't have in our alphabet, we only have 26 letters, and we also have 26 different numbers to represent that. We could represent the whole alphabet, plus 26 because we have uppercase letters and lowercase letters, all right? So big letters and small ones. And well, we also need a way to represent, let's say, this question mark here. So the question mark is 63, and exclamation mark is 33, which is 21 here in this notation, in hexadecimal notation. Now, there's a whole table of letters and symbols, and it's called the Ascii table. So if you look up on the internet, you're gonna see Ascii. So it's like this. You pronounce it Ascii, Ascii table, which defines which numbers are mapped to each symbol. And naturally, there are going to be 250 something numbers, all right? Because that's what you can represent in a single byte. So these folks, they agreed that an exclamation mark would be the number 33. Now we see this dot here, and I want to talk about this dot. So right after the exclamation mark, what comes is a line break. And a line break is nothing more as just a symbol. It's a symbol that represents a line break. So this is actually very important, because I saw already some experienced programmers, they don't know exactly the difference between a binary file and a text file. And they might get confused when you have a line break, right? Because I told you that a file is nothing more than an array of bytes, all right? And this is the array. This file here is this array. It starts here, it goes through here, and then this break here is just because otherwise you wouldn't be able to see it. But if I expand this, you see that it's breaking after, all right? And if I reduce it, yeah, I don't want to, yeah, this is good. So this is just an array of bytes. It's just an array of elements where each element is a number from 0 to 255. All right, this is a file. It's nothing more than that. Nothing more than that. These are the contents of a file. All right. So the file name, for instance, this is elsewhere. This is called a metadata of a file. This is stored elsewhere. But what is inside the file, if you use Ruby's file.read, for instance, which we saw in a previous video, this is reading, what this read here is doing, it's reading these bytes here. It's reading these bytes. There's nothing more than that. So it's really, really simple. You just gotta understand this. So if you think about, here is the hello world, and then there's a dot, and you see that the dot is 0A, but 0A is actually not the character for a dot. And the thing is that, well, we have only so many characters, all right? So we have some symbols like the exclamation mark, we have the question mark. You're going to have also symbols to represent numbers, like from 0 to 9. 0 to 9. And that's it. They're not going to reach 100 symbols. Even it's going to be less than 100 symbols. And the line break is a symbol. It's the number 10 here, and or 0A in hexadecimal. And whenever you have a line break, you have a 0A, or whenever you have a 0A in a file, you know that if you're displaying the text, like in a text editor, you want to do, once you see a 0A, you want to do a line break. That means you want to start a new line. All right. And then after it, so right after it, already comes the other content. So how are we today? And then exclamation mark. And then we have two line breaks. So it's one line break here that goes, oh, sorry. So we are after, this is right after the exclamation mark, all right? And then we have 108, which produces this line break. So the line break that goes from here to here. And then immediately after we have another line break, which goes from here to here, or rather here. So from here to here. And yeah, so that's exactly what a blank line is. This is a blank line. A blank line is just a line that only has a line break after it. And then we already have the alphabet here. And then after it, we can see that we have also a line break, which is here, which is going from this after the Z to the next line. All right. So this is basically it. There are a few more things I want to show you in Ruby, so they will be useful, especially later on. That are two methods. So in Ruby, you can say hello world like this, and this will be a string. And you can represent a character. So if I say a string, let me put this in a variable, it's less confusing. So A is hello world. So A0 is going to contain the H, and position 1 is going to contain the E, and so on. All right. And if I do A0, which is the H dot ORD, so ORD, we're gonna see the 72 here, which is the H, all right? And an ORD is just a number, all right? And if you want to know the hexadecimal representation of that, you can say 2s and then 16, and then you're gonna see the 48 here. So you could also do this for the second character, which is the E, and then you see the 65, and if you just don't do this, you're gonna see that this 65 is 1, all right? And there's also, you can also go the other way around. So dot, if you make a string like f, or let's say I, dot ord, you're gonna see this 105, and then you go to the I here, and you see that it's actually 105. So Ruby is correct. And then you wonder, okay, you see here the V. V is 118. And then if you write 118, you can do also backwards. So you go from the number to which character is that. So that's the method dot chr, which I suppose that it means character. And then you're gonna see that you're gonna have the V there. And then you can go from the V back to the number. And you can do this as many times as you want. Doesn't make sense, but you can. All right. And you can then wonder, like, if the Z, which is the last letter, is 122. So this is a Z. What is the 123? And then you can start finding out. All right, 123 is the open curly bracket. What is the 124? Oh, it's the pipe. And if I type in here a pipe and do ORD, I'm going to see there 124. Now, let me see the hexadecimal notation for this. So this is 7C and it's a pipe. If I go here to the H and type in 7C, you see now this is a pipe. This is a pipe. So it's simple as that. It's simple as that. I know this video is very long already, but that's because I want to explain these things in little details, all the details, so that you can understand. But after you understand this, it's actually very simple. So Z ORD we see is 122, and 124 is the pipe, and then you can keep doing this. You can keep doing this. Now, yeah, now here we reach a limit. We reach a limit. So that's, I'm not going to explain that now, but that is just because 127 is 7f. And the way it's represented in a string is with, instead with 0, x is just /x and then the hexadecimal representation. And then you can see, yeah, you can do these things as long as you want. Also, there are some non-printable characters. Non-printable characters, like the 10. And which one is the 10? Well, the 10 is this one. So the 10 is the 0a, here, the 0a, which is the 10, which is not a dot, because the dot is 46. Now, why, if the dot is 46, why is this 10 here showing a dot? And the reason is because there are some characters which are non-printable. You cannot print them, right? But the 10 is actually a line break, and it's common in, so this is just about this hex editor, and it's common across hex editors that they represent things that they cannot print. They represent with a dot, just with a dot. And then you see a dot, you know, it could be anything. It could even be a dot, and it could be other non-printable characters. All right. So let's say here I could also change it to 7C, and it's going to become a pipe. If I change it to 0A, it's now going to become a dot. If I change it to what is the hexadecimal for 2E is a dot. So 2E is actually a dot, and there's no way we can differentiate it just by looking here. But this is just also a convention among hexadecimal editors. And well, you can keep playing with this as long as you want, and you can try different combinations. You see that all of these are printing dots because they are non-printable. So this is what I wanted to explore in this lesson, and I'm going to stop playing with it now. And on the next lesson, I want to explore a little bit more complex things, like how to represent, I cannot do it, how to represent like a word with a accent mark and other symbols like, I don't know, Japanese characters and so on. So I'm going to explore that, and I'm going to go through the Ascii table, which I encourage you to go and look up on the internet to understand this better. But I'm going to go through that on the next lesson, and certainly you're going to use this on the upcoming lessons. So this is very, very important. This is very basic or foundational knowledge. All right. So thanks for watching. Hope you learned this, and see you in the next lesson. Goodbye.